We live so much of our lives online, sending messages, buying things, logging into our accounts. But have you ever really stopped to think about the invisible shield that protects all of that information? Well, today, we're going to pull back the curtain on that very shield. We're talking about cryptography.
Think about it. Every time you send a WhatsApp message, you're literally sending your private data out into the open.
Or how about this? Every time you log into a website, you're transmitting your most sensitive credentials, your password, across this huge public network.
And of course, every single time you pay for something online, your financial details are just flying through the digital ether. I mean, when you stop and think about it, it sounds incredibly risky, right?
So that's the central puzzle of our modern lives, isn't it? In a world that's built on these open connections where basically anyone could be listening, how do your secrets possibly stay secret? And the answer? Well, it's an ancient art, but it's been supercharged by modern mathematics. This is not a new problem at all. For thousands of years, kings, armies, spies, they've all wrestled with this exact same challenge. How do you send a message so that only the right person can read it? The message itself isn't the problem. It's getting it there securely. So the solution they came up with, and it's the one we still use today, is a process called encryption. And the concept honestly is beautifully simple. You just take readable information and you transform it into something that looks like complete and utter gibberish to everybody else. Okay, so here's how it works in basically 3 steps. You start with your original message, we call that plain text. Then you apply a secret rule, which we call a key. And what pops out the other side is the scrambled, unreadable message, known as ciphertext. So for example, let's say we have a really simple key, like shift every letter forward by 3 places. In that case, hello becomes HOOR. It's just total gibberish unless you have that secret key to reverse the process. That's called decryption. With the key, the secret comes back to life. But without it, it's just noise. But of course, here's the catch. A simple code like shifting letters, that is absolute child's play for modern computer. It could guess millions of possibilities every second. So to secure the internet, we needed much, much stronger digital locks. And right here, this is where the whole game changes. Modern cryptography isn't about clever wordplay. It is built on a foundation of extremely hard mathematical problems, ones that are designed to be difficult for even the most powerful supercomputers to solve. The whole secret sauce here is what you might call a one-way principle. Okay, imagine this. You take 2 massive prime numbers and multiply them together. A computer can do that in a flash, right? Easy. But what if I give you that giant result and ask you to find the 2 original prime numbers that made it? Well, that is an incredibly difficult problem, one that could take a normal computer billions of years. This imbalance, easy to do one way, but nearly impossible to reverse without a secret shortcut, that is the very heart of modern digital security. Okay, so this whole idea leads to 2 main types of encryption. First, you've got symmetric. Think of it like a simple padlock with just 1 key. It's super fast, but you've got a big problem. How do you securely get that single key to the other person? But then there's asymmetric, which solves this problem in a really brilliant way. It uses 2 keys, a public key, which is like an open lockbox you can give to anyone, and a private key that only you have. Anyone can put a message in your box and snap it shut, but only you, with your private key, can open it. This totally solves the key sharing problem. And that, right there, is how we create trust online. When you see that little padlock icon in your browser's address bar, you're not just trusting the website owner, you are, at a fundamental level, trusting the mathematics of asymmetric cryptography. And believe me, its impact is absolutely everywhere. This math is what protects your passwords from being stolen. It's what ensures your private messages stay private. It's what secures billions of online payments every single day. In fact, the entire system of trust that makes the global internet even work relies on the strength of these cryptographic principles. Seriously, without it, our entire digital world pretty much collapses. But hey, this story is far from over. It is a constant arms race, between the code makers and the code breakers. What started with simple ciphers for armies has evolved into this incredibly complex system that secures our world today. And on the horizon, we've got the rise of quantum computers, which threatens to break all of it. And that's why mathematicians are already hard at work building the next generation of defenses, quantum-safe cryptography. And that really brings us to the core takeaway here. See, cryptography isn't really about hiding things. At its core, it is about creating trust. It's about trust between two people who have never even met, trust in a system you can't see, trust that allows our entire digital society to function. So the next time you log in or send a message, just take a second to remember that invisible guardian working behind the scenes. Because in our hyper-connected age, it turns out that pure mathematics itself has become the ultimate and maybe the most powerful guardian of our privacy.